Okay, so let us continue with where we left off, where we stopped rather. Um, so, we saw a brief introduction to the overall domain, and we will again reinforce a lot of those topics during the course. So, our syllabus itself, like all your courses, is divided into 5 units, and the first unit, uh, we looked at some of the overall view of the VLSI industry. We will look into a little bit more detail about some of the terminologies used on a day-to-day basis. And then we will look at a very important topic called as scaling, which tells us how the properties of the circuit change as we go from smaller and smaller sizes. And another part of this first unit, the very important topic which is related to mainly the fabrication. So, like I said earlier, this is an extremely high tech domain. We don't have any commercial fabrication facilities in India, but it's still very important for VLSI engineers to understand the whole process because a lot of the design factors are influenced by the fabrication. So, a very superficial knowledge of the design, uh, we have a lot of levels. We have the gate, we have the circuit, we have the transistor, and even below that, we have the fabrication. So, a good engineer should be aware of all the levels of this overall VLSI design process. The second unit, we will actually mainly look into the transistor, one of the most important things. And of course, like I said, no BJT anymore. We are only going to focus on the MOS or metal oxide semiconductor transistor and the properties of the transistors like current, voltage transfer characteristics, and simple CMOS circuits using these transistors. We will see how to build them. The third unit will jump to another very important aspect of digital design, that is the adder and other data path objects like multipliers. And in digital cores, these are the most important components because they do 95% of the work. The rest of it is your input. Input might be analog, so there will be analog to digital converter. Output might again have to be analog, so might be digital to analog converter. But in between on this, whatever processing you want to improve quality of the input, you want to do some analysis, you want to convert speech to text, whatever it is done by the digital core. And what is there in the digital core? There are not too many things. Of course, there will be adders, and in some very special cores like DSP cores, etc., there might be dedicated multiplier circuits also. So we will only look at these two as part of this unit. We look at some of the more advanced designs for adders and multipliers. Fourth unit, we will come back to the gate level from the system level, and we will look at delay. Very important thing about MOS circuits. The basic requirement is functionality. We have to have the functionality, the gate has to work. Okay, that's fine. But what are the other properties? Like if you want to look at how fast is the clock signal, what is the operating speed that I can have for this particular circuit, then you have to analyze the delay of the circuit. You have to improve the delay of the circuit. And for this, we are going to look at one very important metric called as logical effort. And based on that, there is also a method of logical effort. The last unit, we will look at more circuit families. This is a small typo here. I have to change the text here. I'll change that. Sorry about that. But we will look at different circuit families, so with different properties. And the very last part of this subject will deal with some very basic timing definitions which are used in the industry. Sorry, correct this thing. This is a duplicate slide, so correct information is here. Okay, so we'll directly jump into first unit of our syllabus. First part of the first unit is introduction to VLSI design, and within that also the first topic itself is what is called as the VLSI design flow. Okay, so there are many ways in which we can make an integrated circuit. The objective here is we have a specification of some functionality, maybe given by a design team, maybe given by a sales team, maybe given by some sort of market analysis. But it's a very high level specification in terms of, say, we want a particular DSP chip, or we want a particular 16-bit microcontroller, we want some particular IC for home automation, anything. Okay, and this will have some, maybe it'll have a clock frequency, maybe it'll have bit width, but very less other than that. And from this, the VLSI design flow has to take it and go all the way up to what is called as a layout. That is, it is something that is given to the fabrication, and this steps, layout is a picture. We will see some examples of layout, but a layout is a picture which is rectangles. Okay, and the starting specification is a technical specification in terms of the functionality, 16 bits or 32 bits or 200 megahertz. So how do you go from this specification all the way to a layout? So these steps where the design is continuously transformed from one domain to another constitute what is called as the VLSI design flow. Okay, so we will look at a very uh, high level diagram for this process. Uh, a few things that we can uh, see from the diagram here. The first is that the design, okay, the first and the last we just mentioned, product requirement, which you see on the top here, is in terms of the functionality required that your company or your design team has to manufacture. It might not be the overall IC, it might be something smaller also. It might be a graphics unit. Okay, most modern microprocessors today have a graphics unit. Most have a video processing. I'm not talking about the GPU, but inside that there will be a video processing unit. Before, the more traditional microprocessors just had your, what you learned in computer organization, your arithmetic logic unit, the memory unit, and the control unit. But today, of course, there are, because the functionality has increased so much and so much is expected of a microprocessor, there are many dedicated units inside. So that could be one of those units here, and we go from that to a behavioral bar functional specification. So this is an example of a Verilog code. That is, you are going from a very abstract description in the first step to a very concrete description in the second step. You're transforming it into Verilog code. Verilog code you might have learned in the third semester or fourth semester. Verilog code has a very concrete structure, right? It has an input, means you have to specify what is the size of the input. You have to specify the number of inputs, and inside the body of the model you have to specify what is the functionality. You have to specify what is happening, either in terms of structural code, in terms of gates, or you can specify it in terms of um, data flow statements, or you can specify it in terms of behavioral statements, if then else, logic blocks, initial, always, etc. And that is one of the most important functionalities of the Verilog code also, is that we generally, if you see this keyword here, it says register transfer level, or RTL. And this coding style is one of the most strong points of Verilog. Why Verilog can be adopted almost to any design. There was earlier more popular HTLs have a relatively new history. HTLs, maybe they are around from early 1990s, and the earlier HTL was VHDL, um, VHSIC HDL, and VHDL was a little bit more complicated than Verilog. And Verilog evolved around the mid 90s, maybe around 95, the language reference manual was developed. And Verilog's one of the most important design requirements of Verilog is it should, as far as possible, be similar to higher level programming languages like C or Fortran of that time, etc. So it's easy to code in Verilog, but you have to remember that you're not coding with variables, you're coding with digital logic. So that is one of the most important things about Verilog. It has so many functionalities from high level programming languages, but it is applied to data, bit widths, it's applied to bit type data. And the, that is the first level. You can write this code, okay? But the true uh, advantage of that is this step where we can actually convert. Okay, if this was not possible, then just writing that code and seeing the waveform is almost pointless, and there's no advantage of Verilog at all. The real advantage comes with the number of programming languages that are available in Verilog, plus their ability to be automatically transformed into a gate level description. That is the most important thing, because if you have a say some sort of functionality, so maybe a complicated case statement, etc., it is not easy for you. For example, you might have 10 cases, and for each of those cases you want to do some particular action, and it's not easy for you to do that directly at the gate level. For example, if you sit down and try to code in Verilog, you have to do a lot of work. If you want to directly code at the gate level, you have to have the gate level, what logic you are going to use, what type of gates, and gate, or gate, nor gate, what is the whole decoder circuit should be ready with you before you can actually write the code. But like I said, Verilog gives you something from high level programming languages that gives you the case statement. Okay, so the case statement itself is not so great. The real greatness is that there are a lot of tools which can perform what is written here as behavioral synthesis, which means that we can take that case statement that you have written and feed it to some tool, and that tool will convert the case statement where there's not even a single gate level description into a complete gate level description, okay, in terms of our digital gates. And or not X or mux might be there. If you write something little bit more complicated like behavioral statements, you might have flip flops in the design, but that's not so bad. We have all those gates are well known gates. So this behavioral synthesis is one of the most important reasons why HDLs are completely adopted in digital design. There's no other way you can do digital design except some toy digital design with 10 gates, 20 gates you can do by hand. But beyond that, the real advantage of HDLs is this particular step, which is called as behavioral synthesis. And we'll see this in more detail, of course. And there's a division also here. The blue region of the diagram is called as front end VLSI design, and the gray region of the gray region of this diagram is called as the back end VLSI design. This is just a description that is naturally evolved, but this is also very important for us because in the Indian scenario, that is, if you look at the VLSI jobs in India, the gray is much more common. That is, there are many more job availabilities in companies like Intel, Qualcomm, etc., for the back-end VLSI design. And the reason is that the back-end VLSI design is actually more time-consuming, it's more complicated, it requires literally more manpower. Because if you look at front-end VLSI design, uh, everything happens by tools in backend also. It's not that front end completely depends on tools and backend people are sitting with a scale and pencil and drawing things, etc. No, not like that at all. But the problem is, as we have advanced more and more to the nanometer regions, the physical effects are dominating. So when you're looking at the layout level, which means that you're looking at the actual material of the transistor, not in terms of a circuit diagram or a transistor level diagram. You're not looking at those diagrams anymore. You're actually looking at the fabrication, almost at the fabrication level. What is the material by which the transistor is made? What is the shape of the transistor? What is the shape of the wire, etc.? So when you're at that level, at the nanometer region also, there are a lot of effects that the tools that are there are not yet able to predict. So it's not that the human being is going to predict something that the tools cannot predict, but the human being at least has to use some of his intuitive knowledge to make some decisions and try to improve the result that is predicted by the tool. So that is one of the most important reasons why there are so many jobs in this particular back-end VLSI design. It's also called as physical design. We'll see these steps in more detail, of course. So here the front-end VLSI design produces something called as a netlist. Again, we'll see this, but the netlist is just a series of gates and interconnections. It has nothing about the size or anything, but that is the starting point for backend, where you see the structural description. So we cannot do with case statements for backend VLSI design. Okay, backend VLSI design has to start with a structural description, meaning the description has to be in terms of gates. It cannot be in terms of anything else. So then there is a step called as physical synthesis, which means we synthesize the actual circuit, and that also goes through another step called as physical specification, which we'll see in more detail later. And finally, the output of that. Okay, this is again text file. Text file will have lot of details about the material, about the region, about the interconnections, about the size of the transistors, about the way in which the metal interconnections are formed, etc. And this text file is generally in format like it's called GDS2, etc. Many formats are there, but this GDS2 is the starting point for the fabrication. And fabrication we will see in the second part of this unit also. But netlist is produced as the end of the front end VLSI design. Back end VLSI design produces a specification of the layout in a particular format, for example, GDS2. And that goes to the, that is the only format accepted by the fabrication cannot take gates also. They don't know anything about gates, they don't know anything about digital logic. They only know about materials, because they are all experts. They are all experts in material science, in particular silicon science. So they can take a diagram of a layout and then they can produce that layout in silicon. So that is the last part of the VLSI design flow. Okay. And again, I mentioned this design is refined. Another very important point, I didn't mention this, but one shot. Okay, that is to go from beginning to end, where every requirement. Why are we having these checks here? Okay, the reason is it's not that the tool again is. Maybe I should put this point above. The whole show is completely dependent on CAD tools. Okay, you can be a VLSI design engineer for almost 30 years and not ever use a pen or a pencil. It's completely dependent on CAD tools. But why do we have these checks then? The problem with that is we have to make sure, because the designs are so complex. 10,000 gauge is a very small design actually. In practically, if you look at some of the MTech students and some of their projects that they do in Intel and all these other companies, they might be given a block that has a 10K gauge is very common. Okay, so whenever you have a design that is 10K gauge, things can go wrong. I mean, there is a probability that when converting from a gate level, or when you convert from a behavioral to a RTL type specification, something goes wrong, and this could be because of the coding style or the way the conversion is done. So at every stage, okay, it is very important to do a verification, or what is commonly termed, you might have heard, a simulation. Okay, whatever the level. So for example, at this stage, okay, you're just doing Verilog simulation. That is, you have the Verilog code, you might write a test bench, you see if the functionality is okay, that is this check. If the functionality is not okay, then obviously you have to iterate. If it's okay, then you can go to the next step. Okay, But if it is not okay, you have to modify it before going to the next step. So here, for example, the transformation is completely by tools. There are no engineers who are involved in this transformation. But an engineer has to be there to check that the gate level this thing is given here, but step and so on. But the problem where all these engineers are being impacted in a lot of cases is when the outputs produced by the tools are not satisfying, and in the front end not so much. Okay, so that's why it's not so much manpower intensive in this region, but it's really manpower intensive in this region because here we are actually looking at a lot of very very small sizes and a lot of components, so the effects are exponentially more in the back end VLSI design compared to the front end VLSI design. So a lot of times these checks, for example this check here, okay, timing or power, uh, we'll come back to this later on in the end of the fifth unit. Actually there's one of two things which are called as setup time and hold time, and these are nightmares for physical design engineers because that's what's checking here. Okay, you have a layout, and up to this point that sort of information was not there. Nobody knew what was the length of a metal interconnection. At the end of this step we have a structural specification or a netlist, and that just says that the output of this gate should be connected to the input of some other gate. But once you do this physical synthesis, that particular interconnection will actually have a length and a width, which means that associated with that length and width, you are going to have some resistance and capacitance. And whenever you have resistance and capacitance, it is going to create some delay. So all those delays are what are being analyzed in this check. And if the check is not satisfied, that's where the engineer has to go. He has to make some modifications to the design. Either uh, he has to introduce something called as buffers, or he has to move some of the things. And until this check is satisfied, you cannot say that the design is ready for layout. So this iterative nature of this VLSI design flow is one of the reasons why it takes 2 years to go from one design to the next design. So for example, Intel currently we are at the 10th generation. They've already uh, advertised 11th generation, and it's going to come out soon. But it doesn't come out in 1 month or 2 months. It takes a few months for the design to go from one generation. And that's the reason why. This is one of the main reasons. It takes some time, and we will see this later on also. But each time you want to check a particular design, because there are so many things to check for, it could take anywhere between a few hours to a few days. So that is why labor intensive, time intensive, and tools are very very important. Today you have some tools, right? Tomorrow if you can come up with a better set of tools, and everybody in the design community will jump to those tools because they are better in some way. So tools are very very critical to the VLSI design flow, but digital design, analog design not so much. Analog design is still a little bit more handcrafted, and that's okay for them because the number of transistors in analog circuits is much lower, exponentially lower. There's no analog circuit in the world which has 10k transistors. At most 50, or 50 is a huge design actually. 50 is just too big. Maybe more like realistic will be 30 to 40. But they have a whole different set of problems. So we'll not go into that here. But whatever I'm mentioning here is purely digital. There's no analog or RF components in these designs. Okay? So we'll look at each of these blocks in a little bit more detail, starting with the behavioral or functional specification. And you see the example here. And again, this is one of the most important advantages of HDLs. And again, Verilog, VHDL both are there, but Verilog, in my opinion, is a little bit more um, flexible or easier to use for beginners. If you look at a whole generation of VLSI design engineers, but many people do prefer VHDL compared to Verilog because it has more functionality. So if you're an experienced HDL coder, then VHDL might be a better option. But for beginners, Verilog is easier to start off with. And one of the most important aspects of that is hopefully you have seen some programming language before coming to Verilog. It's not the first programming language of your life. So if you've seen any programming language like C, and a lot of things in Verilog are designed based on the syntax, based on the functionality in C. And like I said, the main advantage of Verilog is you don't have to worry about the gate level description whenever you start off with the design. You can work at a very high level and the code will do the work for you. Okay? So there's an example here. So next we will look at this RTL synthesis. So we're going through this chart here. Behavioral functional specification, we already saw example. Next, we will look at how exactly this RTL synthesis happens. So what that means is you have written some code, maybe with case statements, maybe with if-then. That's also allowed. You can have something like generate statements. You can have behavioral blocks. You can have blocking statements, non-blocking statements. You have a lot of functionality. And this functionality is designed, I mean, whoever designed the language is aware of the requirements of a digital design. Okay, because without that, there's no point in designing a hardware description language. The language has to describe hardware, right? So whoever designed language, they knew that. Plus, they also knew what sort of features are programmers going to be familiar with. Let's try to combine both. That is the intersection of digital design with programming languages. And Verilog is right at that particular intersection. So a lot of people, okay, because of that reason, they not try, but they by uh, by they just the most easy way to code is at the RTL level, and nobody starts coding at the structure level because nobody knows the structure. They don't know the structure of their design, and they know only the functionality, and that's why the RTL level is the most common level. And why it is called as register transfer logic. Okay, registers are memories, right? And logic is when we have some uh, like logical operators and or else etc. And RTL code, if you generally see the structure of the code, it will be in terms of some registers, and the data in the register will be transferred based on some particular logic law. Meaning, if A and B, then A C equal to D plus E. If not A and not B, then C equal to D minus C, something like that. So the data in C, okay, that is the memory, is determined by the logic functions between A and B. So that is why the way in which you write code is called as RTL code, because the whole structure is based on how you transfer data through your registers based on the logic functions. And the advantage of this RTL synthesis, which you see here, you can go from gates, okay, that is, you can go from a statement like this, which is allowed in Verilog. But the RTL synthesis, we won't go into the steps in RTL synthesis now. But if you write something like this, then it knows that it's a mux. This is some sort of, I wouldn't call it intelligence, but you can call it like a lookup table type of approach. That is, if you have a select statement anywhere, okay, the probability that the designer wanted a mux is very high. So whenever you see a select statement, RTL synthesis steps will put a mux there, and that is some way you can describe RTL synthesis based on some lookup table type approach based on certain these things. and or etc. directly, you know that we have gates, so that's not an issue. And even for the synthesis, that is even sorry, even for the sequential blocks, there are some particular lookup tables. So you might have heard of this in Verilog also, but in Verilog, when you write a certain type of non-blocking statement, for example, it will synthesize as a D flip-flop or a register. So those type of lookup table are also there for the RTL synthesis sequential statements. And uh, there's a step that is not there in this diagram, but it's also very important. RTO synthesis, like I said, gives you a gate level description, but the problem with that is it might be very large. So there is a very important step that happens in most RTL synthesis flow, which is called as logic optimization. Logic optimization means, suppose you have some function which has 8 terms. If you can somehow not change the actual logic, not change the actual answer, but change the logic to represent that function by just 6 terms, then that is definitely better. So that particular step is called as logic optimization, and there are many like the K-map is a method of logic optimization. Next level of K-map is called as Coin-McCluskey method. Then there are other logic optimization which are even more complex, called as two-level logic optimization. There are tools like Espresso which do logic optimization. There are many things that are going on before the actual netlist is ready. So the logic optimization is the second last step in the front end VLSI design. So we're still in the front end part. Okay, we have written the Verilog code. Verilog code is being converted into gates by the RTL synthesis, and we have done a logic optimization to produce a very optimized set of gates that is representing your overall product requirement. That is what you see in this step. And after that it goes here, where there is some new terms are there: library and library mapping. What this means is, we have gates, right? So there are no constraint on the gates that are produced in this stage. For example, 8 input AND gate. Okay, 8 input AND gate might be there somewhere, maybe a very complicated structure for your uh, specification. So somewhere the RTL synthesis produces an 8 level AND gate, and logic optimization is not able to reduce that. So the problem with that is, um, has a limited set of books, right? Now, if you want some, it might not be available